Support for today's Heat Treat Radio episode is provided by Heat Treat Bootcamp. Find out how to enroll in this basic training at www.heattreattoday.com/bootcamp. And welcome to Heat Treat Radio. Whether you're listening to us or tuning in via video on heattreattoday.com/radio, we're glad to have you. We're continuing the Lunch and Learn series with members of the Heat Treat Today team. In this episode, the Heat Treat Dr. Dan Herring talks about the role of Austempering in heat treat. We get pretty technical and visual in this episode, so jumping onto the video version of the episode will be most beneficial. In this episode, the Heat Treat Today team includes Alyssa Bootsma, social media editor, Doug Glenn, publisher, Evelyn Thompson, assisting editor, Kieran Ganser, senior editor and associate publisher, and myself, though you may not see everyone on the screen in this round. Let's take a listen.
All right, welcome everyone. We're here with another Lunch and Learn with Dan Herring. Today we're going to be talking about the principles of Austempering. We do these Lunch and Learns really for the benefit of our Heat Treat Today team, and we knew that learning from Dan would also be educational for the entire industry to educate us a bit. So Dan, with that, I'm going to turn it over to you. We're going to try to spend about 30 minutes or so learning about some of the very basic principles of Austempering. So ball is over the fence to you, Dan.
Good. Well, welcome everyone, and it's my pleasure to discuss the heat treat topic that we call Austempering. Doug, let's move on. One of the things we're going to do today is we're going to recall from a previous Lunch and Learn the definition of heat treating. We called it the controlled application of time, temperature, and atmosphere to produce a predictable change in the internal structure, or what metallurgists call the microstructure of a material. So we're going to introduce various words that are related to different types of microstructures today, or these internal structures. But before we do, I've put on the screen a brief definition of Austempering. It's certainly a heat treat process. It's used in medium to high carbon, both plain and alloy steels, as well as cast irons, example being ductile iron. And we're trying to produce a microstructure called bainite, which is probably a foreign word to most of you, and I'll endeavor to explain it in a moment. But to give you just a view from about 30,000 feet, you might be asking yourself, well, what types of products are austempered and why? So I put a couple of examples here. I've put an example of a lawnmower blade, seatbelt components like the tongue and receptacle, and some tractor parts as well. And a good example of this might be the seatbelt components. We've learned to put on seatbelts. In my day, we didn't have them, but now we do. And we all learned to buckle up. If you get into an accident, you discover why your seatbelt is really your friend. We want something that's strong, that if we get into an accident, will not shatter and break. But at the same time, we want something that's tough and slightly ductile, so it will bend and not break. And austempering is a process that's used to produce all the seatbelt components that I'm aware of. Similarly, lawnmower blades, we don't want a blade if it hits a rock as we're mowing the lawn. I don't expect most of the people on the call to have mowed the lawn. But if we hit a rock or a hard object as we're mowing the lawn, we might want that lawnmower blade to get a ding in it, but we don't want it to shatter. And so those are some typical examples. So you might ask yourself, well, why do you austemper? And what we're saying here is that if you need increased ductility, toughness, and strength at a given hardness level, Austempering is right for you. We're typically talking about parts that are in the range of maybe 35 to 55 Rockwell C. We are developing, as I said, a bainitic structure as opposed to a martensitic structure, which is what's produced when we harden a steel and quench it into something like oil or water. So we get improved toughness, and we get some superior properties related to that as well. And some of the properties don't change very much, but they're equal to what we get when we harden a steel, when we get this martensitic structure. But the bottom line is we typically get less distortion. We get better wear resistance. We don't suffer from cracking, as some of the high carbon steels are prone to do. And interestingly enough, with cast irons, we get some what are called improved dampening characteristics, noise and vibration. So why is it important, like for example, in an automotive engine, to have dampening characteristics? Because we want the engine to run quietly. Okay, what types of materials can be austempered? This is just a partial list, but mostly it's medium carbon steels. That's carbon steels with anywhere from 0.5 carbon to 0.95 carbon, or in other words, an AISI 1050 to 1095 grade. We can also do medium alloy steels, the 4130s, the 4140s, the 5140s, 5160s, etc. Certain stainless steels can be austempered, although not many of them. And as I said, cast irons, the example being a ductile iron, can also be austempered. And I wanted to give you some idea of the mechanical and different properties of steel. We talked in an earlier lunch and learn about the fact that steel is an alloy of iron and carbon and manganese. And we add other elements to the mix in order to get various either mechanical properties, chemical properties, electrical or magnetic properties, and certain other advantages. So an example of mechanical properties that we're typically interested in is hardness and strength, brittleness, ductility, elongation, wear, and shock resistance. Now, strength is measured a number of ways. There's things called fatigue strength and flexure and impact strength and shear strength and tensile strength and torsion strength and yield strength. This is a metallurgist's rendition of a teeter-totter in a schoolyard. Now, don't laugh. This is what defines the difference between a metallurgist and a mechanical engineer. For all the mechanical engineers out there, metallurgists draw cartoons. That's the easiest way to say it. Howsoever, at one point in all of our lives, we've probably been on a teeter-totter. And we know that in this particular teeter-totter, we have strength properties on one side of the teeter-totter and ductility properties on the other. And we know that as the strength goes up, the ductility will go down. And as the ductility will go up, the strength will go down. So as a result of this, we decide what we want for properties, and we realize that there's a compromise going on. If we make them extremely strong, they'll be brittle because they'll have very, very low ductility. And if we make them extremely ductile, they'll have very low strength. So this balancing act is what we're trying to do when we look at the properties we're trying to achieve. And if you remember, The microstructure is what gives us these properties. Now, this is something that is not intended to confuse, but I thought I'd add a little metallurgy into the mix because we are going to talk about several microstructures. This is what metallurgists call a time temperature transformation, or TTT diagram. And this is really an artist's rendition of one. There's a lot more information typically contained in one of these diagrams, but for our purposes, it isn't too important. We can use this artist's rendition to get the essence of what we're trying to do. We start off by heating a steel to austenitizing temperature, and that's above the dotted line shown in this particular diagram. So at the very top of those turquoise lines in temperature. And then what we do is we make sure that the component part is uniformly up to temperature. And now we get ready to harden it. We get ready to quench it. And what we're dealing with is we're rapidly cooling. And under normal hardening, you'll notice that there's two lines there, one called MS and one called MF. MS is the martensite start line, and MF is the martensite finish line. So typically in hardening, our goal is to produce martensite. And in order to do so, we want to cool rapidly enough to miss what we call the nose of the curve. Because if you look at this type of diagram, you'll see that it on profile looks like somebody's nose. And the turquoise lines are missing the nose of the curve. Thank you, Doug. Excellent. And as a result of that, we're cooling rapidly. But the difference between hardening and austempering is that we don't cross the MS point. We don't cross into the martensite range. We don't transform to martensite. Instead, what we do is we put the brakes on, we stop, and then we introduce a long soak or hold period. And we cross into the bainitic range of the curve. And so austempering is typically performed about 25 to 50 degrees Fahrenheit above the martensite start temperature of steel. Now, there are some exceptions, but that's a very typical range. If we're not controlling the process properly, we might get a microstructure that's both bainite and martensite. But if we do our job right, we'll get a fully bainitic structure, which is often what we desire. Now, and I realize some of this has words that some people may be unfamiliar with, but we've heated the part up until we're austenitic. We're in the austenite range. And there are three various methods of cooling that can be employed. On the far right-hand side, if we rapidly quench a part into oil or into water, we might produce a microstructure that's called martensite. It's a body-centered tetragonal microstructure. We get something that's very hard, but brittle. That's why we have to reheat it and perform a process called tempering in order to take some of the brittleness away and add some ductility back in. Now, on the far left-hand side, we may slow cool the part rather than rapidly quench it. And we produce a microstructure that is both ferrite and pearlite, the result of slow cooling. So instead of getting something that's very hard, we get something that's very soft. You might say, my gosh, why do we want to do that? Well, we like to do that sometimes because we like to take a steel and, for example, machine it into a final form before we go back in and reharden it. So as a result of that, we form a ferrite perlite microstructure. We're able to machine the part. Then we can go back in and reharden it. So slow cooling gives us a ferrite perlite microstructure. Rapid quenching gives us a martensitic microstructure, and a moderate cooling rate, the one shown in the center, gives us a bainitic microstructure. And bainite is a mixture of ferrite and cementite. Again, words that you're perhaps not familiar with. But the way I like to say it is martensite gives us a microstructure that is not as hard as martensite, but tougher in general than martensite. And we'll explain that as we move forward. But I thought before we do, you might want to see some typical type of heat treating equipment that's used to austemper parts. A lot of parts are done in a mesh belt conveyor line. The one that's shown on the left, where parts are loaded onto a table, sent through the furnace, and dropped at the end of the furnace into a salt quench, which is located in the floor in this particular drawing. Salt is the primary medium that we quench parts that will be austempered in, because salt gives us the temperature range we need to be above the martensite start point. Now, a number of people have asked me in the past, can I use oil rather than molten salt to perform this operation? There are certain oils that can be used at extremely high temperature, but there are fire hazards and other hazards associated with them. So the typical answer is no. Molten salt is typically used to perform the quenching. So you have a mesh belt conveyor system for high volume shown on the left. On the right, you're showing a typical shaker hearth furnace, where what happens is you load parts onto a pan that vibrates, and the parts are moved down the length of the furnace and then drop into a salt quench at the back end. Doug, again, let's move on. And I thought you might want to see some pictures of some stampings and things that are going into one of these mesh belt conveyor furnaces. You see the endothermic gas in this particular picture burning out the front of the furnace, and the stampings moving on a conveyor belt, a mesh belt, in through the furnace. All sorts of different types, shapes, and sizes of stampings. One thing you'll notice is that these parts are typically not single layer loaded. They're loaded perhaps 1 to 3 to 5 parts thick, somewhere between anywhere from a ½ inch to about 2 or 3 inches thick as they're moving through this conveyor belt. And to complete the metallurgy aspect of it, you might say, hey, what type of microstructure am I actually seeing? The picture on the left is a primarily bainitic microstructure with some martensite, and its hardness is 44 Rockwell C. The microstructure on the right-hand side is a combination of bainite and ferrite. The ferrite in this microstructure shows up as white or very light in color. Exactly. And this hardness, because you have ferrite present, is about 36 HRC. So depending on the hardness you're trying to achieve, you will get different types of microstructures. That's the purpose of this slide. Now, As far as molten salt goes, a typical Austempering bath consists of either a sodium nitrate or a potassium nitrate salt, typically in a 50-50 mixture. And this salt is operating somewhere between 300 degrees Fahrenheit and 650 degrees Fahrenheit, depending on, again, the desired, not only the composition of the salt, but the desired temperature that we want to hold to. So I was going to say, let me back up for a second, Doug. So to kind of summarize this, when we're trying to put the brakes on, as we're rapidly cooling down, missing the nose of the transformation curve, we want to fall into this bainitic region. And in order to do so, we need to stay above that martensite start temperature, which for many steels is in the 400 to 450 degree Fahrenheit range. So our molten salts will typically run at 475, 500, even 550 degrees, all the way up to 650. So we pick our salt temperature, not only depending on the salt, but also depending on the temperature that we want to hold the bath in. And some of the reasons for selecting a salt quench is that the temperature of the salt bath dictates the ultimate hardness that we're going to achieve. You might find this interesting if I didn't mention it in our previous Lunch and Learn, but I think I did, that martensite, when we quench into the martensite range or field, martensite is an instantaneous shear transformation. It really progresses at the speed of sound. So martensite forms almost instantaneously. But bainite requires time for the transformation to take place. So a typical time in the salt is somewhere in the range of 18 to 20 minutes. I've seen salts or parts held in salt for as short as 10 or 12 minutes and for as long as 30 minutes. But it depends on the thickness of the part, the material, and ultimately the desired hardness we are going to reach. Now, interestingly enough, as opposed to a part that we harden to martensite and have to retemper or temper to balance the teeter-totter, so to speak, with a Austempering process, we do not need to temper afterward, because the parts are effectively tempered, so to speak, in the salt. So we have a hardening operation that results in a bainitic structure, but we don't need to temper. So that's one of the differences between hardening and Austempering. And again, the time in the salt will decrease as the transformation temperature increases, and the time in the salt is similarly associated with the carbon content of the steel. So let me give you a couple of examples. I mentioned in an earlier slide that 1050 or SAE 1050, 1055, 1075 steel are typical steels that are Austempered. And again, you're Austempering those to put the hardness typically in the range of 40 to 45 Rockwell C. Not nearly as hard as if we hardened and quenched them into oil or water, but certainly hard enough to give you a properly Austempered part, giving you this part that is a combination of good hardness and yet a lot of ductility.
We'll return in just a moment, but first, let's listen to a word from our sponsor. Sign up to go to Pittsburgh this October 31st, 2022. This fall, Heat Treat Today is hosting the first ever Heat Treat Bootcamp, a basic training to benefit new hires and old hires who want to learn more about what the North American heat treat industry has to offer. We're talking the main players, products, processes, markets, and materials in the North American heat treat market. That is, who are the main equipment and service suppliers? What products are they selling? What are the popular processes in heat treat? What markets is heat treat most important to? And what materials are most often heat treated? This is the perfect training to help you walk and talk the industry and will not be overly technical. Go to heattreattoday.com/bootcamp to register for the 3-day event in Pittsburgh. Again, that training is found at www.heattreattoday.com/bootcamp. Now, back to the episode.
So this in a nutshell is a brief summary of Austempering. We've kind of said what it is. It's a process that's going to give us a bainitic microstructure. We've looked at a little of the metallurgy of what we are dealing with here. And we've seen that it's a different type of microstructure than is something like annealing or normalizing, which gives you a primarily ferritic and pearlitic microstructure. And it's different than hardening that gives you primarily a martensitic or tempered martensitic structure. So for those parts that require not only hardness but toughness, Austempering is a process that should be considered by heat treaters. And Doug, that's really the end of the presentation that I've prepared. We can certainly discuss it a little bit more if anyone has any questions.
At the beginning, did you mention because we're talking about perlite and all that stuff? Did we talk about austenite? I mean, did we talk about?
Well, we talked about austenite because, again, that's the temperature to which we heat the parts up to at the very beginning.
Right.
In other words, to start the process, we heat the parts up to the austenite field, if you will.
Right.
In other words, the parts are essentially red hot. They are above the proper transformation point that they turn into austenite.
So I assume that's here on this, if you guys can still see the images, right? That's austenite. The austenitic temperature is up above this dashed line, right? I mean, that's
correct. That's what we talked.
Okay. And then as you bring it down, you're coming through perhaps there's a lot of different ites in heat treating, right? There's austenite, pearlite, ferrite, bainite, martensite. You know, it sounds like a stalactite and a whatever those other things are in the caves. But all of those things basically are telling us about the orientation of the molecules inside the metal.
Well, think of it this way, Doug. When we have a steel, its microstructure, if it isn't hardened, its microstructure is typically body-centered cubic, which means the atoms are all lined up in a certain structure. Now, what we do when we heat it up is when it gets above the transformation temperature, that dotted line for simplicity in this example, the atoms will realign themselves from body-centered cubic to face-centered cubic. And a face-centered cubic structure is called austenite. And then when we quench it, until we move into the nose of the curve or past those red lines, we still maintain an austenitic structure as we're crystal structure as we're cooling. The ferrite, the pearlite and things occur when we cross over into those reddish lines in that area there. And I know this is, and I think you can do this, if we start off as austenite and we slow cool, but slow, keep going, slow, cool. We go all the way down like that. Keep going down. Okay, if we do something like that, and I've got some pictures to show it better, but the idea being the fact that because we've fallen into the nose of the curve, we form a microstructure that is typically ferrite and pearlite. The second line you've just drawn, we would get a microstructure that might be, well, the first line you've drawn is indicative of an annealing process where we're slow cooling inside the furnace. The second line you've drawn is more indicative of a normalizing process where we've cooled at a faster rate, but still, in this case, we've fallen into the nose of the curve because it's not that quick. And to give everyone a perspective of the time element involved here, and I haven't shown numbers, but the time element is for plain carbon steels, you may only have a few seconds to miss the nose of the curve. So as a result of that, you have to move very rapidly where those turquoise lines are shown. You're cooling at a very, very, very rapid rate to try to miss the nose of that transformation curve. The secret with Austempering is that you have to put the brakes on before you form martensite. And that's not as easy as you might think it is. But that's one of the reasons why molten salt is an excellent medium to quench into. Don't mix up crystal structures with microstructures. So ferrite, the pearlite, the bainite, the martensite are microstructures, whereas the crystallographic structures, body-centered cubic, face-centered cubic, body-centered tetragonal, represent how the atoms realign themselves.
Absolutely.
Okay, anybody have questions for Dan?
I was thinking about asking you, Dan, but you had already essentially answered it, was how difficult is it to have that rapid cooling and then control it to remain quite stable for a long period of time? And you hit on the first part of the question, which is, well, the salt quench. It does a good job in this instant. But yeah, how does the heat treater maintain that stability of temperature for such a long time?
Well, that's a great question because one of the interesting properties of salt, molten salt, is the fact that it is a bath that's extremely uniform in temperature. So when, for example, the parts, these stampings and other parts are conveyed through a furnace, they then drop off into a quench. And there's a conveyor belt in the quench under the salt that the parts drop onto this conveyor belt and then move through the salt. So if I want 20 minutes in the salt bath, I have to run the speed of the conveyor slow enough to allow that time to take place. Now, not to confuse everyone, but there's other ways you can austemper. You can heat in molten salt and then quench into molten salt. So there is a molten salt. You can actually preheat in molten salt, have a high heat in molten salt, and then a quench in molten salt. A lot of people don't use that for high volume production work, but they still use that.
Okay.
But yes, you need time in the salt for that transformation to fully take place.
So the let me do a couple of things, and we can probably put this up on the screen, but we just recently, I believe we've already released this, the Heat Treat Radio interview we did with Bill Dissler regarding salt quenching. Okay, that may be of interest to people who have an interest in what about salt quenching. So you might want to reference that sometime. Feel free to look into that. And then you also could just search our website for Bainite or Austempering, and you may come up with some additional articles. So that's it. Dan, thank you very much. I appreciate it. And unless anybody else has another question, I think we'll sign off at this point.
Good. Well, we'll see you next time.
All right. Sounds good. Thank you, guys.
Thanks, Dan.
Thank you.
We hope you enjoyed listening to today's episode with Dan Herring. Heat Treat Radio is on Spotify, Apple Podcast, SoundCloud, iHeartRadio, Podbean, and the website www.heattreattoday.com/radio. If you'd like to get in contact with Dan, head over to www.heat-treat-doctor.com, or you can also email Dan at dherring@heat-treat-doctor.com, or email me and I can put you in touch. My email is bethany@heattreattoday.com. As always, if you have a new or interesting idea that you want to hear discussed on Heat Treat Radio, let me know. Also, if you'd like to sponsor a future episode, let me know at bethany@heattreattoday.com. We were just in Indianapolis for FNA 2022, and if we missed you, we missed you. Check out the industry calendar on heattreattoday.com to mark the dates to attend industry trade shows in 2023, and we'll look forward to meeting you there. Heat Treat Radio would like to thank Heat Treat Bootcamp for sponsoring this episode. Sign up to attend this basic training in the next 2 weeks at www.heattreattoday.com/bootcamp. This and every other episode of Heat Treat Radio is the sole property of Heat Treat Today and may not be reproduced in part or in whole without advance written permission from Heat Treat Today. And I'm Bethany Leone. Thank you for listening.